So first, the first issue is prison. Prism. Okay.
Yeah.
So prism is normally made by glasses. Nowadays you can use plastic or the other kind. Even you can use water to make that shape. So basically, the cross section of this prism is a triangle. Okay. It is it's isosceles. Can you see that? Normally, that is we use these two sides are equal. So can we call this ABC?
Yeah.
ABC. So basically, what you do is net and light coming from the right, from left hand side. Say the just use a different color. And so when the light come, and because that index is different, that is the issue, right? So this is called N1 and this is called N, because if for the air, if for the air and the vacuum, the N1 is equal to 0, equal to unit. By the way, do you know the N? They call the refraction index. Yeah, refraction index. Do you know the definition?
No.
Yes. That is associated with light speed. Do you know the light speed C?
Yeah.
Divided by wave speed of light in the particular medium.
Yeah.
So this is light speed. Speed is constant. Is a constant. Do you know the constant? This particular constant. Yeah, that's right. And this is this wave, this light speed. You can call the wave speed or light in the media. Okay. So light speed is a light speed. In a media, optical media. So it's normally the semi-transparent, like water, like glasses. What do you mean?
Yeah.
So that is light speed in vacuum. So by definition, it's in vacuum. However, because it's in air, there are not much particles. Therefore, the index is also close to 1. You see.
Yes.
This is a very basic equation. I think we need to highlight that. So another basic law is Snell's law, called the Snell's law, which is determined. Perhaps we need to study this before we study prism. We need to study the simpler case where we have two media. All right.
Yeah.
So in this case, if we just call this media 1, doesn't matter. You can call media 2. Doesn't matter. I can call media 2. All right. So obviously, in this case, we have two types of media. So with the light coming from one direction, we have draw this like this one, right? So not only the direction of light will change, but also the speed of change. Well, they are the same reason, all right? Yeah. You can say that the direction change because the speed of light change. Okay. It's getting slower. So the light travel fastest in the vacuum. Okay, whenever into the glass, water, and it slow down. Okay, as the slow down, they will change the direction. You see, they will change the direction.
Yes.
So this phenomenon is called refraction. Okay. There's a simple law called the Snell's law. I use theta 1 here, and this is theta 2, right? And this is the normal direction. Can you see? This is not the force, just normal direction, okay? Yes. Which means this is a perpendicular. So the Snell law says that if you multiply this N1 and multiply the angle sine theta of this angle, okay, then this direction will equal to N2 sine theta 2. Can you see?
Yeah.
Okay. So that is how we derive everything from this basic law here. Okay, you can arrange that. For example, you can say N1, N2 will equal to, if you divide, you get a sine theta 2 and a sine theta 1. So you can write a different form, right? Okay. Now, the difference is that you see once the light travel to that one, when they go out, can you see there's in this case, we can make things more complicated now. Can you see this also, they will continue, can you see?
Yeah.
When they come from more denser media to the vacuum, then they will change direction as well in the same way. And if you have time, you can prove that this direction will parallel to the entered direction. Okay.
Yeah.
And because we are dealing with just two similar, well, so you can argue that because this and by simple mathematics, because these two normal directions are parallel, so these two are equal. Can you see?
Yeah.
And according to, so this angle must be also equal to theta 1. Can you see?
Yes.
Okay. And also another thing you notice that it doesn't matter which light go which direction the light goes. Okay. The light go travel that direction, which is okay. That can be described as the path. However, if you consider light go that direction, it's the same. Can you see? Doesn't matter which direction they go. So that is something you need to know. Okay, now return to the prism. The only difference is that in this case, these two surfaces are not parallel. Can you see?
Yeah.
Therefore, there's no simple relation that this angle, can we call this angle theta 4, right? And there's no, in this case, theta 1 is equal to theta 4. However, in this case, it's not necessary so. Why? Because there's another angle to be considered called alpha, right? And today I just draw your attention that we can draw, how do we work out the formula for this one? We can, first of all, we can just draw the normal direction. Can you see? I can draw the normal direction here. Can you see? Yeah. Once we draw the normal, probably use different color. We draw one moment. So we draw the normal direction, can you see?
Yes.
And based on this, because this is, perhaps we can also make this color, use some coloring here that just highlight that this is a different media, can you see? So the index will be different. Normally it's larger than air, okay? So in this, should this happen, and then we should be able to work out the direction of the light after enter the first surface. So this is theta 1, can you see? And theta 2, according to our analysis here, the light will change direction towards normal direction. Can you see?
Yeah. Yeah.
Towards normal direction. Okay. So that is that's part of a story. Now by the night, then we can draw another normal direction over here. Can you see?
Yes. In
this way, we can also apply Snell's law to solve this puzzle. So basically that's enter. This is theta enter the. I just draw the one angle. Okay, that is enter that surface. And can you draw? Are you able to draw? Can you draw the light path after they come out from this surface AC? Yes, that's good. Yes. So you can, if you have time, you can work out what does the direction change. All right. I think we have to be careful when we are not go too far. All right. So that is why we are not just start prism for this. We have to see how this type of what type of question will be asked based on this knowledge. All right. And based on my analysis, probably they will not ask you to prove that. But if you have time, or if we have time, we can prove that the change in angle can be determined. Can you see? Can you call this beta? All right.
Yeah.
So that
can you calculate that using the Snell's law? Is it not?
Yes. No, you have used the trigonometry. You use the Snell's law. Yeah. You just based on Snell's law. Just bear in mind this also is N1. Can you see? This also is N2. It's N1. Okay.
Yeah.
Okay. It's up to you. This is just the introduction today. All right. So the important thing is you have to learn how to use this formula. This is very important. Okay.
Yeah.
Now let's quickly go to the what we call the probably two subjects now. So because this is two. Okay, this second issue that's the third issue, and the fourth one. We're starting the total internal. Okay, total reflection. That is a internal total reflection. Okay, so this normally we discuss this issue in the context of optical fiber. You know that the optical fiber is the quickest to transfer the signal, electrical signal, internet, right? So that's why the cable, if you use optical fiber, and that would be very efficient, very fast. So if I draw this, if I use a similar connection, can we just consider this? Can we just consider this is a cable, all right? This is cable. You can imagine this is just a cylinder, all right? It's a cylinder. So the light will travel from this. Light will come in. Can you see? Light will come in, and they will. Can we just assume if light have already entered? Perhaps one moment. I found more space here. I'll probably draw the diagram over here. So in this way, we just assuming the light has already entered that cable, all right? So that this is the direction of travel of signal. You see, so basically that is in signal. The signal goes that way. The signal goes that way, and what we assume that if there's a light coming like this one, can you see the light is traveling? One of them traveling towards that direction. Okay. Now, this time, can you draw the direction of the maybe more, make it more, let's just draw this one. Okay, I draw this side. Okay, I make the angle slightly different angle because I want to show you how to, yes, and in the meantime, we also draw the normal direction, you see. And this, so something will happen, okay? Both reflection and refraction will happen, all right? Can you draw the refraction if assume that N is larger than outside? Can you see outside, can we assume the outside is N1?
Yeah.
And to make the question simple, can we just call it, can we just assume outside the index is equal to 1, like air, okay?
Yeah.
Make it simple. And inside the index N2, we just use N, okay? Sorry, not 2, but N, okay? That will simplify our formula, all right? So the question is, how can you work? Can you draw the refraction light after, say, for example, this could be the optical, this is glass, okay? Or this is a fiber, is optic fiber. This could be the glass, right?
Mm-hmm.
This outside is just air.
Yeah.
So can you draw the direction of the refraction light?
Just refraction, but not reflection.
Not reflection, just refraction. Refraction.
Mm-hmm.
So refraction is not come out.
Yes.
Reflection will, yeah, that's right.
Because I remember learning from last year. It was on a physics course, and it says that the light traveling from one object,
more condensed, yeah,
from one medium to another medium,
yeah,
can both reflect and refract.
Yes, that's right. Yes, that's why I ask you to. Actually, I can draw reflection for you. Can you see?
Yes.
Reflection will be. We just put this upside down. Reflection will go that way. That's right. This is reflection. Can you see?
Yes.
So in this case, this is refraction, because the total internal total sorry, yeah, that's very interesting. We are talking about how much that total. The idea of total reflection means that under particular condition, only reflection occur, no refraction.
Mm-hmm.
To understand why that's why we need to work out the direction of the night path first, okay?
Yeah.
Because in this case, obviously, the incident night can be divided into two parts, can you see?
Mm-hmm.
If this is incident angle, you see, this is angle
Yes.
of incident, and that will this is refraction, can you see? So that will be the refraction. That's reflection. Sorry, this is reflection,
yes. Mm-hmm.
and that will be refraction. Can you see?
Yes.
That becomes refraction. So refraction is a different idea. Refraction. Okay. But in this case, obviously, this angle is larger. Can you see? If I call this is in our notation, this angle must be larger. Can you see?
Yes.
Can we call angle 1 here? You see?
Mm-hmm.
This angle, we can call angle 2 if you wish.
Yeah.
Okay. So therefore, if we increase, so basically, if I write a Snell's law here, if we apply the Snell's law, we can get this equation, right? So we got, because is n1 is 0, so we only have a sine theta 1 equal to n multiply sine theta 2. Can you see?
Yeah.
Can you see that? Can you see that?
Yes.
So that now we are interested to know. So basically, in this case, we can argue that the theta 1 is larger than theta 2 because n is larger than 1. Do you agree?
Yeah.
So therefore, if I increase the incident night here, can we just, yes, if I increase the incident night here, okay, what would happen? If I increase this angle, what would happen?
It would increase as well.
So that's right. So that yellow path will increase like this. Can you see? Just use different color to highlight. It is a refraction.
Mm-hmm.
That will go that way. Can you see?
Yeah.
Now, if I continue doing so, there must be existing a special value at which there is no refraction at all. Or in other words, refraction will be always follow the surface. Do you agree?
Yes, I got it.
You got it?
Yeah.
So that angle, when this happens, we call it the critical angle. You see, I just highlight this angle. In this angle.
Oh, everything comes back to me.
Yeah. All right.
Yeah.
So in this way, there's no, that's why we call the total reflection, because the refraction is transmission, you see.
Yes.
If the refraction goes through the cable fibers, which means that there's no transmission. No transmission means no loss.
Mm-hmm.
Does that make sense? So therefore, you can see that is why we wish to work out this angle. The red angle is called the critical angle. So the red color one, you see. Yeah. So from this equation, we just need how can we do that? We set up theta 1 equal to theta 1. We set theta 1 approach to half pi. Can you see? When this happens, that theta 1 is half pi. Can you see? Does that make sense?
Half pi means it's 90 degrees.
90 degrees, yes. Half pi is 90 degrees.
Yeah. Mm-hmm.
So in other words, you can see origin is here. As the incident angle increase, they will go like this. Can you see?
Yes.
So eventually they reach 90 degrees. That's a maximum. Can you see?
Yeah, but why is it approaching but not equals to?
You can assume it's equal. Yeah, eventually we're equal to. Yeah, eventually we're equal to. So when this happens, so basically, yeah, mathematically, yeah, we're equal to that one. So you can realize that easily. Now, if you apply another condition is here, is that if you just, in this case, theta 2 will approach to the critical angle.
Yeah.
Can you see that?
Mm-hmm.
So you can say, you can more, I use this arrow to indicate the process, all right? But eventually actually equal to, yeah. So as a result, can you rewrite this equation? Can you rewrite this equation under these two conditions?
Yes.
That is these two conditions.
Mm-hmm.
What is 90? By the way, what is the sine 90 degree in numbers? It's a spatial angle.
One.
Yes,
One.
that's right. You can. That's why you can simply write 1.
I can't cross it out. Oh, I can.
You just
I did.
undo or redo.
1 equals to n sine c.
That's right. So in this way, we got this important equation. You see, that is a critical angle. Critical angle can be written, or I'll just write a sine first. Sine critical angle. Sine critical angle. We're equal to 1 over n. Can you see?
Yes.
Or in other words, and the critical angle can be solved by use inverse sine 1 over n. Okay.
Yeah.
So this is condition when the total reflection occur. It's happening internally, so that's why it's called the total internal total reflection. So that is idea.
Yeah.
Okay. So
I got it.
yeah, sometimes we may use this all. It all come from the Snell's law, right?
Yeah.
Of course, the company. If we don't assume that n1 equal to 1, then we still can we still can got something similar. All right. Okay, it's that is a 2 idea. Let's have a look. What is your note first? So that is a property of a prism and the optical fiber, and we have done that. Okay. Now these critical angles, these n2, we have assumed n2 equal to 1. Okay.
Yeah.
So that is okay. Now let's just call the circuit now, the DC circuit for filament, diode, capacitor, net dependent resistance. Okay. Perhaps we also will include Ohm's law. Do you agree? Have you studied Ohm's law?
Yes, I think so.
Because that is the basis for this circuit.
Yeah, I understand circuits, but I'm just not sure what those components does.
Yes. Well, that's why we need to see some real questions. All right. We need to see some real questions. But as a summary, because this is so another issue today. Another issue is DC circuit. It could be AC, okay, because they got a capacitor. They ask you. So this is just DC and AC. Do you know the AC?
I'm not sure what
alternate current. DC is direct current. The current is always positive, is one direction. AC is a change direction. We will see, okay? We'll just write down this as a category, secret. So the simplest one is just the battery. You see, you know the notation?
Yeah.
The battery. And then we got a switch. And then we can put some node like the battery here. You see?
Yeah.
So that is the simplest. Circuit. So this is a battery. Normally, this is the direction of this is a positive.
Yeah.
And this is the R resistor. And if you switch on, and the current will go from the positive to the negative. You see?
Yes. And
there's a simple. The Ohm's law is in this. Ohm's law is developed to describe this the current and also the voltage. You see, the voltage of the battery is V. Okay.
Yes.
And also this, when you study circuit, you have to learn how to redraw this circuit based on, for example, this circuit can be easily redrawn in this way because we can see where this is battery. Okay, this is resistor. This is resistor, and you apply the voltage here. Can you see? in this way, I don't have to draw the battery, but we still know that this is there's a voltage across this resistor.
Okay.
So from here, if the current, if you want to measure the current, of course, this is just part, this is still the part of this circuit, right? So if you just continue to draw that, I can change the direction of battery now. Just probably draw here. If I just follow our notation, okay, we can still redraw this one. So we put a negative here, positive here. Can you see that?
Yes.
And the voltage, or voltage means the potential difference. Can you see?
Yeah.
And the voltage of the battery were equal to the voltage across the resistor in this case.
Yes.
Okay. So there's a simple relation between the current, is the direction, and the voltage and the resistance.
Yes.
So that is Ohm's law. So first is Ohm's law. Ohm's law says the current were proportional to voltage across the resistor. Remember, Ohm's law is only applied for single resistance, right?
Okay.
Okay. So that is very brief introduction. Another is a power. Okay, power formula. Electrical power.
Yes.
Power means how much energy, by definition, which how much energy or how much heat is generated per unit of time.
Yes.
That's by definition. But in this particular case, P will simply equal to the current multiplied voltage.
Voltage. Yeah.
Okay, you know this formula, right?
Yes.
If you combine these two formulas, then you can generate several formula for power.
Mm-hmm.
Okay, I will just write the. If you know how to do, we're not go that far. Okay, Ohm's law and power formula, and again, we are talking about a single resistance. Okay.
Mm-hmm.
Now, very briefly, then we can go to the, if we have the more than one resistance, what would happen? So that is, if you have more than one resistor. Okay.
Yes.
In this case, then we have two formula. One is the effective resistance, were equal to the sum of the individual resistor. Another is a reciprocal of effective resistor, were equal to reciprocal of this sum. Can you, have you seen the formula before?
Yes.
So this formula, one is called the series configuration. This is called a parallel.
Yeah.
Parallel. I just go through that. So that return to our question. For example, actually, this diagram is come from one of the exam.
Yeah.
Of the test, PAT. So that's why if you put the resistor like this, okay.
Mm-hmm.
Okay, like this. Can you work out the effective resistor? If this resistor is 1 ohm, so this is a 2 ohm, and this is 3 ohm. This is a 2 ohm. This is a 5 ohm. Can you work out effective, the equivalent resistance? When I say equivalent, which means we can use a single resistor, RE, to represent all of these resistors.
The resultant. Yeah.
Yeah. Do you want to try?
Yeah, it's quite challenging.
It's challenging. Well,
Yes.
in that case, I make this simple smaller, because ultimately you are going to solve this problem. All right. Can before you go, before 1 moment, I make this a simpler. Okay.
Yeah.
I make this not too many difference. 1 moment. Just rewrite this one. So I just put one resistor here. So I put this is just one here. You see that is also 5 ohms.
Yeah.
So how do you solve this type of question? Yes, that's right.
That's it?
No, have a reciprocal. You have a reciprocal here. Got it?
Yes.
Yeah, you have reciprocal. Otherwise, the unit is not the same. Can you see? Oh, by the way, that is some idea of the unit. So it's a unit of the quantity. Unit, ，okay, so that's very important. And this is also called the dimension, okay, dimension. In physics, it's called the dimension of the unit. So how do I know your formula is wrong? Because the unit, so that is notation for dimension. The resistor, if you're looking for the dimension, that we use this bracket to denote the dimension. And which means they just say what is the unit of resistance. We know it's ohm, all right?
Yeah.
However, if the dimension of R, 1 over R will be, can you see?
Ohms.
Yeah, 1 ohms.
Yeah, 1 ohm.
Okay.
Yeah.
So therefore, this unit will be ohm -1. Can you see?
Yes.
So that's why I know, that's why we know why this formula is not right. Okay. Now, by the way, this is a very important idea. We can discuss more about the dimension. Okay.
Yeah.
The dimension of unit. That's a very important idea. This is called a dimension analysis. If you have unknown equation, okay, you can first to judge whether this question is wrong or is correct or wrong by checking their dimension on both sides.
Yeah.
Okay. Now, a general approach of this kind is that can I show? Eventually, you have to learn how to redraw this diagram, this circuit. Can you see? So what we can do first, I can redraw this diagram as 1, 2 ohms. Okay. I can reduce this 2 as 2.5. Can you see? Can you follow me?
Why is it 2.5?
Because you see, because they are two identical.
Yes.
They're just like water, like a water pipe. Okay. If these two resistance are equal, so therefore the current go two direction will be the same.
Yes.
And also, besides, if we use this formula, can you see?
Yeah, it makes sense.
It makes sense, okay. And this table, then after that, you can find the total. You can find the effective resistance. You see?
4.5.
Does it make sense?
Yes.
So first of all, we can simplify this, okay, into one. Second, we can reduce this 2 into 1. You see?
Yes.
So it's that's why I say you can learn that to redraw the circuit. Okay. Now that is for the resistors. But a capacitor is not the issue. Okay. Have you started capacitor?
I'm not sure. Maybe I forgot.
Yeah. Capacitor, sorry. Electrical capacitor. Capacitor. Okay. And the unit is a Henry. Henry is for the unit. So what is capacitor? Capacitor is made by two parallel. The notation of capacitor is this. Can you see? Have you seen this notation?
No, maybe I didn't learn.
Yeah, that's for the first time. Actually, this notation also give you the structure of this plate. So basically, they just put the two parallel metal together, metal plate, see, conductor, for example. So if I draw the 3D diagram, that the capacitor can be simplified as a two, you see, two parallel plate, you see. And the gap between them is called D, right?
Mm-hmm.
And just bear in mind, these are made by metals, you see.
Yeah.
So if you put this, if you connect that with the battery, this is positive, this is negative. Can you imagine that?
Yes.
So if you, this is because it's positive. So the positive charge will go that direction, you see? Go to this side.
Yes.
Evenly, okay, and the negative charge will go this side because they are attracted to each other.
Yes.
Okay, as a result, they will form the electrical magnetic field. Have you studied electromagnetic field?
Yes.
Okay, that is how to form the uniform. And also this magnetic field is also uniform. Can we use E to represent the magnetic field?
Mm-hmm.
Sorry, electric field, sorry, not magnetic field, electric field, all right? So you can imagine that this, because in this setup, simple setup, and the voltage is provided by the battery, you see, the V, all right?
Yes.
Because this conductor, so the conductor has no resistance. So when you start the circuit, you have to treat all the wires as a superconductor, which means no resistance.
Mm-hmm.
Therefore, the voltage across the battery will equal to the voltage across these two terminals. Can you see? Can you put
Yes.
V plus and this is V minus? Okay. In other words, the potential difference. So V take V1 equal negative, will equal to voltage. All right.
Yeah.
So this is called the potential difference.
Mm-hmm.
Potential difference. If you just use a single letter, that's called the voltage. Right?
Yeah.
Okay. So voltage represents the potential difference. Okay. And also this diagram can also be simplified just in many cases. If you don't want to draw the 3D diagram, we can simply draw this diagram. Can you see?
Mm-hmm.
Okay. So this is very useful diagram. We can use this diagram to solve many application problem. Can you see? So normally you can imagine there's a battery here or two. You see?
Yeah.
That is a very important devices to generate a uniform electric field. In this case, I only draw electric field, right?
Yeah.
So this is from positive to negative.
Yes.
That's uniform.
In this case, does the current go through? Is a conductor?
No, no current.
Yeah.
Because there's a gap, you see?
Mm-hmm.
Unless there's metal. So this is different from resistors, can you see? Resistor is different. You can put the resistor side by side, you can see? If you put the resistor here, so this is a battery, you can see this is, we just draw this. If you can imagine resistor is just a cylinder, right?
Mm-hmm.
Okay. That the situation is different, can you see? And we have a good conductor here, but we still, the inside the resistor is still conductor, but not as good as wire, you see.
Mm-hmm.
So therefore, in this case, the current will always go through, okay?
Yes.
Go through that. However, these in these devices, you only see the current go at the very beginning with the when you first, for the first time, when you switch on, this circuit, can you see?
Yeah.
So you can imagine that the once you switch on, and the positive charge will go all the way to that direction, can you see?
Yes.
And then stop. Now, if I use a time-dependent diagram to describe this charge move, so can you draw this diagram? If I use this current to describe this, so this is current as a function of time, Now this is 0. So before you switch, when you switch off, there's no current, right?
Yes.
Now, if I switch on, can you draw the graph to describe the current?
At a certain point, or
just time dependent. Yeah.
Is it a straight line?
It's almost straight line. Yes. No, eventually they got a 0.
Oh.
Imagine they will go like decay very fast like this. Can you see? Because the electron cannot go through.
Yes.
See, the charge is here. They cannot move. They cannot move. All right. Unlike the resistor, when you switch on, the current just go to the resistor constant. You see. Doesn't matter. We'll talk about this later. All right. So because the charge can only move from the battery to the plate, conductor plate. Oh, by the way, this device is called the parallel plate. It's called the 2 parallel plate. Plate. Okay, this is a very important device. Okay, what we can do? We can use this to change. For example, can you imagine if the charge particle come, if the positive charge come, goes all the way from outside, what would happen? Can they still keep the direct straight line motion?
Oh, you mean it conducts?
Yeah, if the charge coming from this outside, if the can you call the charge Q? And this is the electrical field. When they enter to this gap, this area, what is any force acting on this charge particle?
It will go through to the negative plate.
Yeah, they were. Do you mean they will bend this way? Do you agree? Do you know why?
It's attracted by the
negative
charge.
Yeah, that's right. So in other words, the force, to be exact, the force acting on the charge inside this area will be like this. So that would be the force. Can you see? The force will be downward. Can you see? So this arrow will represent the force. A little bit crowded here. So F, maybe I draw this one. We don't have to draw. I draw a larger one. It is, by the way, this is a very important device. You see, sometimes in the problem they tell you that they can create the electrical field uniform. Yeah, I just make it larger for you. It's uniform, okay. And then there another one. So if they have the charge particle coming, could be positive, could be negative, all right?
Yeah.
When the particle come in, they will experience electrical field. In this case, it's downward. Okay, it's downward. And there is a simple formula to describe it. So this force, this is a field. Okay, the force, this is Q, the charge. There's a simple formula. The force it will equal to Q multiplied E. Do you know this formula?
Yeah, I think I learned it.
Oh, good.
Parallel plates part.
A parallel part, yeah.
But before that, I don't know what's capacitor. Yeah.
Here you can consider the capacitor is the same as 2 parallel plate. Okay.
Yes.
Although in real case that because we cannot build very effective capacitor. By definition, capacitor means they can accumulate certain amount of charge. Yeah. That's all. Okay.
Okay.
So this motion. So the motion of this positive charged particle will be the same or project motion near the surface of the Earth.
Yeah.
You see that? So if you just go to the projection motion, have you started projection motion now?
Yes.
So if, for example, this is this is y direction, this is x direction. So if you have the in this case, we just assume theta equal to 0, all right? That's called horizontal projection. So you will see that the trajectory will be like this. Can you see?
Yes.
See, the reason is that there is a constant velocity there after the cannon. There is a constant force is downward, which is gravity. Do you agree?
Yes.
And which is also the constant. Okay. I just put this formula here to compare with these formulas. The gravitational force is equal to the mass multiply the field strength. You see?
Yes.
So this, if you put these two formula here, it's very similar. Okay, this is we call the Coulomb force. Okay, that is a Q multiplied E, and for the gravitational force, I put the G here equal to mass multiply the G. Similar. Can you see? Another piece of knowledge is this, that if we know the voltage across these two plates, you can see, if you apply the voltage across these two plates, and then we should be able to work out the field, electric field. In this case, electric field can be simply written as the voltage divided by D. So this is another formula we can accumulate, all right? So that's why sometimes if they say, well, if you apply the voltage, and then we can work out this electric field strength. Okay. Once we go to, if we can work out the field strength or the force, then we can calculate how much work is done. Can you consider another issue? If this is if we originally this charge is over here, all right? If I want to use the force to move this particle upward, okay, from this position to this, from this position to this position, how much work must be done? Because in this case, electrical force is downward. Do you agree?
Yes.
So therefore, this is the electrical force. We have used external force, at least equal to this force, right? So according to the work done from here to here, the work done will equal to the force multiply the distance. Can you see the D? Do you remember? This is D, the gap is distance D, all right?
Yes.
So this is work done.
But when when FC equals to the applied force F, wouldn't the charge be staying in the middle position? But
I'm talking about two scenario. So this is story one. This is story two. I'm not talking about this particle. We know this particle will go that way.
Yes.
We are just assuming, perhaps we'll go to the next one. We just assuming what would happen if we just move a charge from negative to positive. So it's a different scenario. We just consider another question. Can you see? Yes. If this is a positive, can you see? And we know that we have to overcome the force. Therefore, we have applied the force like this. Can you see?
Assuming the FC is overcome.
Yeah, we assume, of course, in the meantime, there is a force downward because it's attracted by negative side and repulsed by the positive side. So our interest is that we need to know how much work is done, because first of all, we know the force. So this force must be equal to, at least, right? Equal to this force, downward force is QE, right?
Yes.
So this also must be QE. We just consider the least effort, smallest effort, okay? We just move it very slowly. So by definition, the work done by the force by the force F, right, is equal to the force multiply the distance, okay, delta x. In our case, delta x is d.
But how would it move if the resultant force is zero?
Yep, that is a sort of experiment, because we're trying to work out the minimum amount of work done. But normally the force is larger. In other words, by the time if the force is larger than this one, if F is larger than QE, then at here the charge will have kinetic energy. The gain of velocity. Do you agree?
Yes.
Extra, if you do more than necessary, that velocity will larger than zero.
Yeah.
It's a sort of experiment, not a real experiment.
Okay.
Because when our objective is to find the formula, okay? So if substitute our formula here, F is exactly equal to QE, right? And X equal to D, all right? Do you remember relation between the E and the D? So in this case, if this is voltage,
E equals B over D.
Yeah, that's right. Can you combine these two formula? What formula can we obtain? So this is formula. Can we introduce this formula? We can rewrite E, can we?
Yes.
As a V over D multiply D. So that is very important formula. That's the Q multiply V. So work done by this force is equal to the Q multiply the voltage. So this is very useful formula. Very useful formula. I just highlighted this one.
Okay.
Oh, okay.
Yeah.
So in other words, is the work done. So that is important. So work done by F, by the force F is the product, right? Product of the charge, electrical charge, and the voltage applied. Can you see that?
Yeah.
Perhaps we can simplify this story. For example, if you have, this is probably more interesting example. Can you imagine this time I just draw this vertically? Okay. What we do is we just apply the voltage. I just highlight these two vertical plate. So we just put this battery here. In this case, I want to accelerate it. I want to accelerate, not decrease. What I do, I want to accelerate that. You see. So what do? I put this for the filament. Can you see? If I put the filament like this, in this way, here I can make another small battery. This battery just like to make this getting hot, so that they can generate electron. You see? Maybe I will draw different. Let's try again. So that is, if I just can we just consider the vacuum tube? Okay. 1 moment. Can we consider the vacuum tube? So inside there's no air. It's a vacuum tube. And what we do, we first build a small source of this is like the filament. You know, our lamps is made by filament. If you just use connect with a battery and you switch on and getting bright, right?
Yes.
In the meantime, they can generate the electron as well. Okay.
Why will heating it up generate electron?
That's called because on the other hand, the electron to put it this way, if the probably this is not this case. Can we just draw this I think today we will not go that complicated scenario.
Okay.
Can we just, I want to demonstrate the idea that in the first case, we'll assume there's external force, right? This force is external.
Yes.
Okay, is external. However, we can consider the work done by electric field, okay? So this work done by external force. Now we're talking about work done by the electric field. Does that make sense?
Yes, but isn't it the same?
Voltage. Yeah, it's the same. Yeah, if you consider minimum, can you see we do if we consider work done by electric field, we don't have to consider the minimum. That is exactly how much work it is done,
Yes.
because that force is constant. Okay, we don't have to consider the minimum voltage. So in this case, the formula is exactly the same. Can you see? Work is equal to Q. According to the work energy theorem, the work done will equal to the change in the energy. Okay. In the simplest case, can we consider the kinetic energy? For example, if the charge is moving, okay, for some reason, charge is entering to this uniform field. You see? Well, now I'm talking about accelerator. You see?
Yeah.
So if I just assume this is there's a hole, we can draw the hole in a plate. So we now this charge move from one place to one side to another. Okay. Now in the meantime, we put the voltage here. This is a negative. Okay, this time we'll make sure it's correct setting. So this is a positive and negative. Can you see? So if the charge already entered to this area, we know there is a force. Will accelerate that. Can you see?
Yes.
So eventually, the initial velocity is u. The final velocity when they come out, can we call it v? Right?
Yeah.
So if we apply this voltage here, then we would expect that work is done can be calculated by this formula 1. Can you see? And this work done is also equal to the change in the kinetic energy.
We added together.
Yeah, afterward. So therefore, we can got from this simple device, we can assume that the change in the kinetic energy will equal to from this one, we can work out this formula that is a QV will equal to delta E K. Can you see? So this is accelerator.
Doesn't mean the work is doubled in this case because
no, there is no external force, not doubled.
The
reason, the first example, we assume there's external force because we want to work out in this case, because go opposite, can you see? This time we move the positive charge from negative to the positive. So therefore we have overcome that electrical field force.
Yes.
Now in the accelerator, we just let the charge be accelerated. Starting, of course, starting from negative to positive terminal.
Yes.
Also other way around, so from positive.
Positive to negative.
Yeah. Okay. So that is how to I think. So this is a very quick introduction.
Yeah.
To the capacitor. All right. Capacitor can therefore we can use the capacitor to either store the charge, or we use the capacitor to use the capacitor as accelerator. Does that make sense now? We can if you have charge, if the particle is too slow, okay, and we can apply the voltage so that after a while the velocity will increase, right?
Yes.
So their kinetic energy, the kinetic energy increase if you put into the accelerator. You see, it's called accelerator. That's the voltage. As long as the force is towards the direction, not against it.
Yeah.
Okay.
Yeah.
So if we just return to your notes.
I have a very basic question about
Yes,
circuit.
go on.
So is the circuits we've drawn for this topic DC or AC?
At the moment, it's DC.
Okay.
It's DC.
So, and does AC go from negative to positive?
Yes, that can. Probably our because let's just one moment. Let's just go to the screen. Yes, good question. So, and as you can see, we cannot we can only discuss the DC if so this is DC circuit, the difference between AC. So this is DC, this is AC. For the AC, the current is always constant, you see, as a function of time. So this is current and also voltage. So current is a constant. If you draw the, once you switch on, the current become constant. If you watch very carefully, you will see, well, probably there is also a very short period that built up from zero when you switch on. You agree?
Yeah.
And also they switch off. There's yes, that's right. That is you are talking about the real DC circle. However, for the AC, the current can go either direction. You see, so this is quite this difference between these two circles. So you know the current can go like a sine wave, like this one.
Oh.
So you can see you can either positive or negative.
Does it always go like this?
Well, AC is AC. This is simplest AC. Of course, sometimes AC can be a combination of several sine waves. Now, I just probably draw some related circles here. So this related circle we use today is this. Can you see? We can discuss this R, okay? Yeah. And we can also discuss we can also using let's just consider in this way, if we just apply the capacitor here, right? We can only expect that maybe this could be discussed in this context. If you use AC, it basically it's time dependent. Okay, if you use AC, it's battery here, is a switch here, and perhaps we can also put the resistor here. So this is called RC circuit, okay, because that involves resistance and also a capacitor. Okay. In this case, we would expect this is in general. In this case, the current become time dependent. Okay. So the current, if you switch on, the current will from the very high and to zero. Very short time. It's called a transient. So the current will change very quickly.
Yeah.
In other words, in DC, DI dt, if you use a calculus, right? Well, so you can say DI dt is always equal to zero.
Zero, yeah.
And for the AC, DI dt is not equal to zero.
Okay. And for the DC circuits, how, because electrons are negatively charged, how are they like just go from positive charge to negative charge?
Oh, this is another issue. Is convention. Okay, a good question. In the conductor, you are talking about the real conductor, right? A real conductor, there's no positive charge moving, right? So if you want to draw the real conductor, can you see? Can you draw this conductor here? So this is resistor. If you really want to see what's going on in the conductor wire, it is electron which go opposite. You see? So electron is actually go opposite. So this is electron. Electron is actually go that direction.
Yes.
Okay, that's right. That's what we call the charge. This in this case, this charge. However, according to convention, that's different. We assume the current goes that way.
But isn't current the definition is the flow of electron?
No, the current is direction of positive charge move. But in metal, only electron move in opposite direction. However, if you do you study chemistry?
Yes.
Yeah. That makes sense. If you just consider this is electricity, this is positive, this is negative, right? Negative. So therefore, again, there are two directions of current. One is a positive ion, one is negative ion. All right. So we must choose the direction for the current. So in history, people choose the direction of the positive ion. That is why we keep this notation, this convention. When we start conductor, in the conductor, there's no positive charge, but a negative electron.
Yes.
Okay. So both movement of charge, negative, positive, will create the net. So the charge is a net charge, okay? The definition of current is this, can you see? They will descend, so maybe you have positive charge, move that direction, all right? I'm talking about in the liquid, can you see? In the solution. And also some positive and negative go that direction, okay? Now, if these amounts are equal, the current will be equal to 0. The current will equal to net charge, can you see?
Oh.
The net charge divided by time. That is the electrical current. And in the metal, it's simple. In the conductor, we don't have a positive charge move. We only have electron move, all right?
Yes.
So that is equivalent to say that we don't, because this direction is a man choice, we choose, okay? There's no reason why we use the opposite direction to describe the current in conductor.
Okay.
Okay, we're going to stop here now. We'll see you Wednesday.
Okay, thank you.
Yes, we'll catch up. We'll catch up with content, but also I suggest we probably will spend some time to look at the real papers next time.
Okay. Yeah.
Okay.
Thank you.
Okay.
See you.